Okay. What is a critical number?
When the slope is 0 or undefined.
You hear that? Say it once again.
The slope is either 0 or undefined.
Okay. It's an interior point of the domain F at which f prime at c equals 0 or it's undefined. See, just exactly what he said. Okay. That's called a critical point. Any questions about that? Okay, here's a theorem. And this is what we were talking about yesterday and trying to get this down. Okay? Theorem 4.2. If f has a local min or max value at c and f prime at c exists, then f prime at c equals 0. Okay? If there's a local max or minimum and this thing exists, because up here it says it doesn't exist, okay? So you have noticed that distinction. Then it's equal to 0. Now we're going to talk about that necessary and sufficient stuff from yesterday. Necessary. A local min or max at C necessarily implies what? What does that imply?
C is a critical point.
C is a critical point. Okay? Any question about that?
Okay.
Go ahead. Yeah?
So if C is the local min or max, it is also the critical point? Like it has to be the critical point?
That's what we're working at.
Because it's equal to 0 at minimum or
Okay?
So
So it's a critical point. Okay? Now we're looking at sufficient stuff. That's where you're going to. Is a critical point at C sufficient to imply that it's a max or a min?
No.
The answer is no. Okay? Now, let's take a look at that a minute. It says, is a critical point, and that's, the critical point is what we get up here. It's either this or this. And so I'm going to draw it this way. I'm going to go like this, and then I'm going to go like this. Okay? And now that's a critical point. You with me on that?
but it's not the maximum min.
It's not a max or minimum. Okay? Now you see a little bit about this necessary and sufficient. I'm not quite finished with it yet. Okay? How they go in terms of the logic. You did some of that work in algebra or in geometry, looking at that. Okay? Seeing what these do. Yeah, go ahead.
Okay, so a max or min is the critical point.
Oh, just a second. It's tricky. I'm going to say what
okay, so the local minimum and max are always going to be a critical point, but the critical point does not have to be the local max or min.
It's like squares and rectangles.
Yeah.
Square's a rectangle, but a rectangle isn't a square.
Yeah. I like it. Did you follow? Okay. You really finished what I have up here. And that is this. What is a converse of this theorem?
I don't know.
That's kind of what you were saying. Why don't you make your statement? You say the first statement you just said a while ago, if you can remember.
A local minimum maximal is a critical point.
Oh, okay. Now she's going to do the converse.
But a critical point is not always a local max or min.
Mm-hmm. Mm-hmm. And is the converse always true? And the answer is no. Okay? The second part is what you said was the converse of this theorem. Okay, at that point, you have these, but you don't have a local max or min. Okay? I hope that's a little more helpful in terms of looking at critical points. Okay, now, let me just pull some stuff together that I have here. It's not what I want. Page 216. There's a problem there that I assigned, and I really like it. But I found you guys didn't do very well on it. It's 32. And let's take a look at that thing a minute. Okay? Page 216, problem 32, okay? This is what we have. We have an object that follows this path, okay? And it's going this direction at 30, is it say feet per second, okay? It's going this way 30 feet per second. And it's actually shot up at an angle here, which we will probably explore a little bit more detail in terms of that angle and what's happening. But at this point, we're at 10. And so we have two vectors here. We have this vector, which is the boring one that's just going 30 this way. But this one going this way is changing. Here it was pretty high, but now at this point, I'm just going to draw the vector this way. This is what we're going to find. And as these two work together, it follows this path. Okay? Now, this one's going at a constant rate. This one is changing because of gravity. It's going to stop it here, and then it start going the other way. Now, he gives us a very nice little function. And let's see, did I want to use a y? Yes, I wanted to use a y. Y equals x times 50 minus x. Very, very friendly little function. And this thing will generate this curve. And that is 50x minus x squared. Okay? Now, this thing right here is known as dx dt. Okay? And that's a constant. And this is where x equals 10. And I would like to know how big this vector is up here. That's my dy. Okay? And this is what I want to find. How big that is, that's going to be dy dt. And that's what I'm going to try to find. So here I get to work. What is the derivative of this with respect to t? dy dt, right? What's this one? I don't go here, I'll just go right over here. It's much easier.
Minus 2x.
Okay, no. This is going to be 50 dx dt. And this is going to be minus 2x dx dt. Okay? Now, I know a couple of you got it right, but most of you had this wrong. And I don't know quite the reason why, but that's okay. You see what we have here. Now, this is what I want to find, so all I have to do is plug it in at this point. So this is going to be 50 times what?
30.
See, it's right over here, that's 30. And that happens to be 1,500. Okay, minus 2 times
10.
Okay, 2 times 10 times
30.
30. So 30 times 20, which is equal to minus 600. So that's going to be 900 feet per second, and it's in that direction. Okay, so you know where it is. Any question about that? Great physics stuff. And like I've said a number of times, often you don't take physics the first semester in college because you want to get the first semester of calculus in first. And you can do a lot more with it, and it becomes more meaningful. Okay, the next one, he says, I want to find out what happens when we're over here at 40. Okay, that's over on this side, 40, over here. Okay, so we are going to find out what dy dt is there. And now notice, 40 is just going to be straight across here, so what would you think? This vector is still going to be 30, and now we're going to go down. And I'll bet it's going to be the same value as this one, dealing with some symmetry, but let's see if it does, if it works for us. This is still going to be 50 times 30. That hasn't changed. Minus 20 times 40 times 30, which gives me 1,500 minus 2,400, which equals a negative 900, and then using your units feet per second. Is that cool? Not hard, and I hope very descriptive of what we can do with this. Okay? Any questions about that? Okay. The next one we're going to do two ways, and that's on page 209. And a couple people who aren't here, I wish were, because they've been asking questions about this. And also, what I'd like to do, maybe you can help me with a little bit with this. I don't have a total good idea of what the author is asking in terms of what's this good for, okay? This is problem 29. See that? And I do have B on my computer, but I don't believe I'm going to go there with it. I'm just going to look at part A. And we're going to look at it two ways, okay? One we're going to use inverses, and the other one we're just going to not do it without inverses. And we have a very tall building here, which is going to be 150 meters high, okay? And we have a boat out here coming this direction. He's coming this way. And we have an angle over here. And we're going to talk about that angle in a minute. And again, anytime in calculus we're doing an angle, it has to be radian measured. Degrees doesn't make sense. Okay? And we're going to take a snapshot at this when we get to 300, or no, 500. Okay, that's going to be a little value there we're going to pick up pretty soon. Okay, now, this is what it says. A boat sails directly toward a 150 meter skyscraper that stands on the edge of a harbor. The angular size, theta, of the building is the angle formed by lines from the top and bottom of the building to the observer. What is the rate of change of the angular size? Take a look at this a minute. This is what he wants. He wants d theta dx, not d theta dt. Now that puzzles me a little bit. And he defines it for me, but I still have a little bit of a problem. What is the rate of change of the angular size? Okay, the angular size. And then he says what it is, d theta dx, when the boat is coming. It's going to be negative. Now, I'm going this way, and I look at that building, and I'm getting closer, and this is going to go up, and this. I have trouble just visualizing what's happening. But I can do the math. The math isn't any problem. Now, when we're finished, maybe one of you can kind of explain what's happening here, because this is going to turn into a negative. This is going to be coming this way. And this is going to, this is getting bigger. This is getting bigger, and this is smaller. Okay? And we're looking at this ratio. Okay? Now, let's do it with inverse functions. Okay? So the first thing I'm going to do is just write this down here. This is the tangent of theta equals, it's going to be 1,500 or 150 meters over theta, or over x. You see this? Now, here's where I want to talk to you about this a minute. This is tangent theta. I want to get rid of the tangent, and I can't just cross it out. It's stuck there, okay? And because this doesn't say d tangent theta, it says d theta. Okay, so I've got a little bit of a problem there. And talking about that issue, notice this. That theta is measured in radians, but tangent theta is measured in meters in this case. It's going to be a meter idea, okay? Or really a number, I should say. It's a number when we take a derivative of it. Okay, now, let's solve this thing first, just with knowing this at this point. What I would like is this to come out. And so, what is the derivative of the tangent? Okay, like this. And what's the derivative of this? Oopsie, I messed up. I want to go d theta dt. Or dx. Got that? Just about forgot it. Now this side I have to be careful too. I should do it wrong, but I see if you catch it. What's the derivative of that?
150 times.
Is that right?
What?
Okay. This here is 150 x to the negative 1. And we're going to find the derivative of this, which gives me a negative 1. Okay? Times 150 x to the minus 2. There it is. Questions on that? Okay? Now, this gives me, like this, equals 150 over a negative x squared times, divide both sides by secant, so I'll put secant squared theta like this here. Any questions on that? Okay, now we just have to do some crunching of numbers. So this is going to equal, let's just write this over here, maybe it's still helpful. Minus x squared, I'll put a cosine, can I do this?
Sure.
Instead of this down here, it's up there. Any questions on this? Okay, before I can get started and I'll pick it up in a minute. I'm going to go over here. Here's 150, and there's going to be a negative, and that's going to be 500 and another 500. Got that? That's this and this. Now what is this? Cosine squared theta. Well, that's going to be equal to the adjacent side, which is 500, over like this here, and I have to square this. It's this side over this side here, which is going to be the square root of 500 squared plus 150 squared. Are you with me on that? Got that?
No.
No? Okay, we'll go back here. We're just going to call this side A. So cosine theta equals 500 over A. Okay? And A
So
is
you
equal
see
to
the
this.
Pythagorean theorem on the bottom.
You got it. This here squared plus 1500, or 150 squared. Okay? Now, I'm going to take this here and square it. So this is going to be on the top 500 times 500. Oopsie, one more zero here. With me? Question on that? Then, on the bottom here, this whole thing is squared, so it's going to be times this thing, which is 500 squared plus 150 squared like this. Okay? Now, I would like you to crunch the number for me in a minute. This one cancels with this one cancels with this one, and so now I just have this. What does that number turn out to be? It's going to be a negative number. And I'd like it crunched because we're going to do it a different way in a moment, and I want to see that you get the same answer. 0.00055. Now it's going to be in radians per meters.
How? That doesn't make sense. That it's going down.
Yeah.
Shouldn't it be going
Okay,
up progressively?
Yeah, and okay, now, I'm going to, see this is in meters. Let's just do this for a moment. Let's go in here about 100 meters. Okay? And now we're this way. Okay? Now, what we're doing is taking the ratio of theta to this length here. Now you notice, okay, I have a little bit of an idea of it. I don't know if you do or not. We're taking the ratio of this theta to this length. And this length this here has gotten shorter faster than this one here. So that ratio is a negative. But why would I want that? I don't know. It puzzles me a little bit. Okay? Okay, now, is this still fairly much focused here?
Yeah.
I'm going to leave it that way because I can do this problem a lot faster the other way. Now watch what happens here. I've got this, and I'm going to write this now in inverse notation, okay? And that's going to be,
Tangent inverse of 150 over x.
pardon?
Using a tangent inverse of 150 over x equals theta.
I'm going to first do it this way though, I think. I'm going to write this cotangent theta equals x over 150. Now I have this on the top. I don't know if I have to do that way. It's just now, I had been doing it that way, and so I want to continue, okay? Now, I'd like to take the derivative of both sides. Oh, then finding this derivative is a little easier. Now, just a second here. Oh, now I'm going to change this to like this. Cotangent inverse, like that, you with me, of x over 150 equals theta. That's old stuff. Changing these two around and use the inverse. Okay? Now, what does this turn out to be? If I took, we did this one the other day. Tangent inverse of x equals theta. What is the derivative? What is dy or d theta dx equal to? We said that was going to be 1 over 1 plus x squared. Okay? Will you go with me to page 205? 205. We haven't done many of these problems. Okay? Now, on page 205, theorem 3.22. Notice this one here is the second one in the left column. Okay? Now, notice what the one is right across that. That's this one right here. Right here. This one's the inverse cotangent here. The derivative of that is going to be this with a minus sign in front. Just a minus sign in front. Okay. Any questions on that? Okay, so what does this turn out to be? I would like to be the theta dx. The derivative of this side is that. This side becomes 1 over 1 plus x over 150. Are you with me? Square. Thank you. Square. Okay? Pardon?
Why is these cotangent instead of tangent?
That's a good question. I was wondering that too a while ago. Oh, I do know. And the other part is, at this point, I have a mistake. The reason is that I have x on the top. Okay, and it will work the other way. Okay, by the way, I have a mistake here. You find that for me. Not putting this x over 150, that's not the mistake. There were two mistakes. There's still another one. What's that?
You multiply by 150 over x squared.
Actually, okay, I need the derivative of the inside here.
Yeah.
I need the derivative of this inside chain rule. Okay? I got this, but I also need here 1 over 150.
No, I think.
Why? What is the derivative of x over 150? And this is like that g prime of x. That's going to be 1 over 150. Chain rule. This isn't just an x. This is x over 150. Okay, now, look what happens here very quickly. This is pretty fast in many ways. Minus 1 over, this is going to be 1 plus, that's going to be 500 squared over 150 squared times 1 over 150. Okay? Now, crunch that. I did think I was going to run out of space. I did. This turns out to be the same number as this right here, and I wanted to keep that on the screen. Let's go and get that a minute. Okay? Oh, this is ugly. I don't have enough space here. This is equal to, here's a minus 1, and this is 150 squared over 150 squared.
Got the
With
same
me?
answer.
Pardon?
Got the same answer.
Oh, very good. Okay, this has to be
And what-
both squared. Now, after you do it, pretty soon you'll see we have got about the same thing as we have here in terms of the numbers. Okay? Now, notice that this is squared and this is squared, and it could go way up at the top. So I'll put this as 150 squared at the top, like that. That's this here. And then this bottom is a bracket like this. This is 150 squared plus 500 squared, like this. And then this is 150 down here. Okay? Now, look what we have. This one, this 100, this is 150. This 150 cancels with that one. Okay? Now notice what we have here. 150, see that?
Yeah.
And this bottom is just like this. Now, you crunched it.
Yeah.
Good crunching, okay? Because some of you won't, when you get over here, it's good enough that you can just crunch it. But I did it, it also showed you how the two are alike. Okay? Okay. Anybody,
I still get the 1 over 150.
okay.